Hello, I'm Zohreh Davoudi from the University of Maryland. I'm going to present 3 lectures on finite-volume formalism for Lattice QCD as part of lattice gauge theory for high energy physics traineeship course. So in the first lecture, we're going to focus on how to define quantum electrodynamics QED in a finite volume. Before doing that, we're going to talk about what general motivations are there for defining these quantum field theories in finite volume and what are some of the considerations. And we'll talk about QED in particular in finite volume, and we discuss why QED with periodic boundary conditions in a finite volume is problematic, what are the associated pathologies. After that, we'll present some solutions to these pathologies to be able to define quantum electrodynamics properly in a finite volume. We will then turn into computing observables with at least one of these solutions, one of these formulations, and we'll see in particular how the mass of the hadrons get modified when they are in a finite box. And we'll talk about other observables as well. And then finally, I'll just briefly mention what are some of the ongoing and progress in lattice QCD and QED calculations at the moment. Okay. So let's talk about why in general we need to think about finite volume quantum field theories. Well, the answer is obvious. Our computations in lattice QCD are finite. As a result, we perform these calculations on a finite volume with a set of boundary conditions on the fields. And it is important to know how large the volume effects are and how we can correct them. Okay. So it turned out that we really are dealing with 2 distinct situations when it comes to volume effects in lattice QCD calculations. The first situation is when these volume effects are essentially contaminating the values of observables. In other words, they are small, they're under control, but we have to know what they are. Sometimes we have the ability to know analytically what those volume corrections are and be able to either subtract them out or extrapolate them away so that we can get infinite volume values of these quantities. And this is often the case in the single hadron sector and in special cases in multi-hadron sectors, such as when we deal with binding energies. And we will see why that's the case throughout these lectures. But I think probably a more interesting situation is scenario number 2, and these finite volume effects are not actually a curse, they're a blessing in a sense that they would allow us to be able to define certain infinite volume observables using lattice QCD calculations that otherwise we would have not been able to. So the fact that we're limited to finite volume calculation can allow us to access quantities that otherwise we would have not been able to. And these are, for example, scattering and transition amplitudes in multi-hadron sector. So this would be the topic of essentially the 3rd lecture in this series. So we will get there. Okay, so this is really the motivation for trying to understand finite volume effects when it comes to various quantum field theories of interest in nature. And for that purpose, we really care about in 2 different scenarios. One is quantum field theories that have infinite range. So this would be quantum electrodynamics, QED. We're dealing with the photons that have 0 mass, and as a result, they're exchanging an infinite range force in QED. And therefore, we have to be able to define properly such a theory in a finite box because we are going to modify the infrared aspects of this quantum field theory. On the other hand, QCD, while it has massless gluons in the theory, when it comes to low energy degrees of freedom, we only deal with confined hadrons with a finite mass. And as a result, the range of interactions are finite. So we're really dealing with a different situation compared to quantum electrodynamics. And the question is how volume effects are different compared to the QED case. Okay, so We're going to talk about exclusively QED in the first lecture. We'll talk about QCD in the single hadron sector in lecture number 2. And we're going to talk about QCD in two hadron sector in lecture number 3. Okay. So let's talk about QED in a finite volume. Let's understand why there may be problems with defining quantum electrodynamics with periodic boundary conditions in a finite volume. Okay, so to set the problem, let us consider a cubic volume. Okay, let me get straight this. All right. We have a cubic volume, and we're dealing with a special length L throughout this lecture. And then we're having periodic boundary conditions imposed on the fields. Okay, so this is our setup. So what would be the problems with this setup if you consider infinite range forces? Okay, so let's think about the Gauss's law. Okay, the first thing to notice is that the Gauss's law turned out to be incompatible with QED in a finite volume with periodic boundary condition. And in other words, charged particles cannot be enclosed in such a volume, right? So there is a very intuitive way to understand why that's the case. Let's think about Gauss's law. What Gauss's law is telling us is that the divergence of the electric fields over some volume is going to be equal to the flux of the electric field coming out of the surface by the mathematical Gauss's law. And then that is essentially equal to the charge by this electromagnetic Gauss's law, the charge that is enclosed inside the volume, okay? So then you see that on one hand, if I think about the flux of the electric field, in a situation when I have periodic boundary conditions, that's got to be 0, because at every surface, if I have an electric field that is pointing this way, there's got to be the electric field that is pointing in the same direction as I go from one side of this periodic box to the other, just by the imposition of periodic boundary condition. So that means that by periodicity of the fields, I cannot really enclose any charge. And then how do I deal with situations when I really have to define these charges inside a volume with these kind of boundary conditions? So that's the question. Well, let's understand where really this problem comes from. It turned out that this problem is a result of, let me get rid of these. So this problem is really resulting from the 0 mode of the photons. Let's think about the action of QED, okay? So the action of QED, as you all know, is written as sum over space and time of -1/4 F mu nu plus E times the charge times psi bar gamma mu A mu psi. So F mu nu is the familiar field strength tensor in QED, and A mu is the vector field associated with the photons. And then psi and psi bar are the fermionic fields, and the Q is associated with the charge of that fermion, okay? So let's think about classical equations of motion that would arise from such a QED action. We said the variation of action equal to 0. If we do that, then we end up with the following expression, as we all have worked out in our quantum field theory course before. And you realize that I'm dealing with a finite volume. I am not setting the time in this case to, but we can set the time also to be finite. Let's just consider that situation. Then essentially what we have when things are in a finite volume is I can go to a Fourier space with respect to one of these fields that come out of this variation. And that means that because I'm in a finite volume, then this Fourier space is defined by a sum over momenta where these momenta are discretized because of the periodic boundary conditions, and I'm dealing with the sum as opposed to an integral. And this is the remnant from the previous line, the integral over time and space. And as I said, I only took one of these fields, whether outside, out of this first term, or from this delta A mu, and I made it a Fourier component with this transformation, okay? And then I just keep the rest in terms of the x and t, all right? Now, by Gauss's law, or by equations of motion, this variation should be equal to 0, okay? And now we look at this expression and see that it is really the k equal to 0 term of this expression that is going to give us the Gauss's law. Recall, the Gauss's law is really this expression equal to 0, if you work that out. So this is exactly the divergence of electric field being equal to the charge associated with the fermions in the theory. Okay, so again, the Gauss's law is arising from the k equal to 0 mode of this object, because for other values of k, you can imagine that this form would oscillate, and there is no guarantee that only this term is supposed to be 0 for all values of variations of a, unless we really don't have this oscillatory factor, so that we are certain that this term should actually be equal to 0, which is the Gauss's law. Okay, so again, this is from a mathematical perspective. From a physical and intuitive perspective, this is easy to see why the 0 mode is responsible for the Gauss's law. Imagine that you have a charge that is sitting at the origin, and then you have a measuring device far at infinity that can measure the flux of the electric field at the surface far at the infinity. If you add all these fluxes, then you can deduce what the value of the charge is far away at the origin. Why is that? Because there is a 0 mode associated with the photons, with the carriers of the electromagnetic force. They can actually propagate freely all the way to the boundaries and tell you about information about the charge, okay? So if we didn't have the 0 mode and we were dealing with a gapped theory, then the situation would have been different, okay? So that's really the reason that if you try to only define this theory in a finite volume and try to define a Gauss's law, you run into a problem. There's another way to see where the problem arises, which is a bit more mathematical, but I think it's important to also talk about these problems in the language of some remnant symmetries of the action in finite volume with periodic boundary condition, because then you can really understand from a mathematical perspective what the problems are and be able to devise solutions that will remedy those problems. Okay, so let's talk about this. So then second way that we can see the problem with QED in a finite volume is to notice that the Laplacian of QED is not invertible, and that means that we cannot really define properly a photon propagator in a finite volume with periodic boundary conditions. Okay, so let's understand this. So consider the QED action. Now let's consider the Feynman gauge. Okay, so the QED action is as a function of vector potential is, and this is just a pure QED action, so I'm not talking about matter fields at the moment. We'll talk about that in shortly. Okay, so the action is the sum over space and time of -1/4 f mu plus this term, which is added to the action such that we have sort of an action in the Feynman gauge, as you probably have seen in your QFD course. Okay. All right. So let me erase this bit. All right. So now this action can, in fact, be written in the following form. It's just a simple math to realize that we can express the same action in the following form. And now I want to go to momentum space. I want to consider the Fourier modes of the A mu and write the same expression in momentum space, okay? If you do that again with 1 or 2 lines of algebra, you would be able to see that the action has the following simple form. Sum over all momenta, k squared, which is the 4 momentum k squared, and then sum over all components of the Fourier a mu as a function of k squared, okay? And I have defined this Fourier mode, a tilde, as following, with the following convention, all right? So now we see either from this expression or the expression just in the position of space that the photon propagator is nothing but sort of inverse Laplacian acting on the delta function x minus y. And I can write this again in momentum space as the integral over k over 2 pi to the 4, 1 over k squared, delta mu nu, and then e to the I k x minus y. All right, so this should be a form that is supposedly familiar for many of you. And you look at this and say, well, this is infinite volume physics. I haven't talked about finite volume version of this yet. If this is an infinite volume, even though the k equal to 0 mode seems to be singular, that's not a problem, because really this is a set measure 0, and therefore this is not a problem in a finite volume. It really doesn't contribute to this continuous integration. And let's now talk about the finite volume counterpart of this expression, okay? So in infinite volume, there is a well-defined photon propagator, and depending on whatever gauge, you can get rid of the gauge redundancies and all the infinities and singularities in defining the action using the Faddeev-Popov procedure, and all of that, okay? So now let's consider the finite volume case with periodic boundary condition. Okay, so what does that mean? I want to consider, again, a hypercube of a special extent L, temporal extent T, and therefore the momentum modes are going to be discretized as 2 pi n mu over L, where n mu is simply an integer, okay? And so a vector with integer component. So now if I decompose, or if I write the Fourier transform or inverse Fourier transform of a mu x, I have the following form, okay? With understanding that the integral over x is now limited to a finite volume as well as a final temporal extent, okay? I'm not assuming any discretization. We're not talking about ultraviolet effects in this lecture, only the IR effect. So let's consider everything is continuous in a space and time. I'm just putting a finite extent for both position and time. And therefore, a mu x, written in terms of the Fourier mode, is going to have the following form. It's the sum over discrete values of momenta of these a mu tildes and e to the I k x, with understanding that the k, again, is discrete, all right? All right, so let's go to the next page. And continue. All right. So now let's just try to write the action of QED in a finite volume. So the procedure is pretty much the same as before, except that now you're going to see that instead of having this integral over momenta of k squared and sum over a tilde squared, we're going to have a sum over discrete values of k, and the free factor is 1 over TL cubed with our convention of Fourier transform. In this case, then the propagator can be simply seen to be having this following form. It's going to be, again, now the sum over this discrete value of momenta. By short, I just note this as this t to the 4. And then we're going to have 1 over k4 dependence in this function. Now, you're going to see that this is problematic because now we're dealing with a sum. Even one term being singular in a discrete sum is going to be problematic. And therefore, the propagator of this photon in a finite volume with periodic boundary condition turn out to be ill-defined, okay? So let's try to have a deeper look into this problem and understand where this issue comes from, right? Because it kind of looks similar to the issue of gauge redundancy in QED in infinite volume. If you remember, where we wanted to define a photon propagator, starting from the action of QED, we'll see that we end up with a non-invertible sort of Laplacian operator for the photons. And in order to fix that problem, we resort to Faddeev-Popov gauge fixing scenarios such that we can remove all these equivalent configurations of gauge fields from the action, okay? So the question is that, is there a redundancy here that we have kind of introduced back into the theory by thinking about periodic boundary conditions? And the answer is actually yes. It turned out that now we're dealing with the shift symmetry of the action, okay? What does the shift symmetry mean? Let's look at this equation down here. It means that if I take my A mu and then change it by a constant value, I'm going to normalize that constant value by 1 over the volume of space and time, and B mu is essentially just a constant in both position and time, then this, in fact, is a gauge transformation, because I can imagine having some lambda as a function of x and t. This is both x and t. And once I take the derivative of that function, I get this constant function, okay? And the action is really invariant under this shift symmetry. And if you think about, let's get rid of these. Now, if you think about the momentum space representation of that condition under this shift symmetry, we go from some A tilde of k to A tilde of k plus 2 pi over EQ times some constant over L if mu is equal to 1, 2, 3, and mu over T when mu is equal to 0. So why do I have this instead of B mu? Well, M mu is proportional to B mu. We'll see the reason for these prefactors and redefining these mu in a moment. But in any case, this is just a simple Fourier transform. If you think about doing the Fourier transform of a constant with those prefactors that I've defined, then you get essentially a contribution only from k equal to 0 mode for that constant term, and the rest is in the following, okay? Why do I have a form like this? Well, a form like this, with this proportionality to this integer mu news, is because I want this to be still a gauge transformation, obviously. Meaning that if I have a matter field that would transform under this gauge transformation with the following factor, e to the I e q lambda of x, then with the definition of the lambda of x, the derivative of lambda x is actually this b mu factor, then it is easy to see that this lambda of x should have the following form, right? And if you look at this form, which is proportional to t or x, and that's the reason that we get a constant out of this derivative for the shift transformation, is that now if I put it over here and then transform my x by x plus L and transform t with t plus capital T, then everything remains invariant. Remember, I'm dealing with periodic boundary conditions. And because of the periodic boundary conditions, the values of both matter fields and the gauge fields should return to itself as I periodically change the x to x plus NL and t to t plus n times capital T, okay? So this is a form that would satisfy the periodicity. It would satisfy gauge invariance, right? And therefore, we have this shift symmetry in this finite volume theory. Well, recall that this shift transformation is not really a symmetry of the infinite volume case. The reason being that the A mu fields need to vanish in infinite boundaries, okay? But in fact, it turned out that this kind of reappears, right, in the finite volume theory because of these periodic boundary conditions, as we saw from this explicit consideration over here. So what that means is that although you have an action, right, that gets contribution from all these A mu fields, an infinite number of shift transformations or shifted A mu fields are there that from the perspective of action, they're equivalent. And therefore, we're kind of counting for this infinite redundancy, right? So it would be great if we can try to come up with ways to gauge fix, meaning that we could get rid of this shift transformation invariance in defining our propagators, right? So that already would tell you that a procedure similar to Faddeev-Popov procedure in QED in infinite volume might be able to fix some of our problems here, which is something that we're going to discuss next. All right. So let me clean up this and go to the next page. Okay, so we're going to do this. We're going to see how we can modify the theory in such a way that we don't have to deal with these singularities in the zero mode, be able to not have to deal with the problem of Gauss's law, and not have to deal with this sort of redundant or redundancy, infinite redundancy in the representation of the theory given this shift symmetry. All right, now there are multiple solutions here. There's not just one, but rather multiple. Let's talk about a few popular ones, okay? So the first thing that comes to mind is that how if we just get rid of the k equal to 0 mode. By k, I mean 4 momentum k. So all the photon modes are there, except for the one that corresponds to k equal to 0, all right? And this is a solution that sometimes is called QED-TL subscript in literature. And this is really the first solution that was proposed to be able to get rid of this problem. And as we will see, this is really a direct outcome of performing a Faddeev-Popov gauge fixing condition, okay? And this is the topic of exercise 1. And it's not that hard because if you just go back and remind yourself how the Faddeev-Popov procedure works for gauge fixing, you should be able to follow this procedure that is described here, okay? So we're gonna impose a gauge condition. Remember, this A, B field is the shifted field. So I have an AX that is shifted by B over T times L. Now, I'm gonna add this factor, which is essentially equal to 1. This is the integral over finite space and time of this shifted field A, where the shift occurs with this constant B, and introduce this function, delta function, that imposes that these configurations are equal to 0. The shifted configurations should be equal to 0, and therefore I can insert something that looks like 1 into my action. So what you need to do to go back to the path integral definition of QED using the action with periodic boundary condition, insert this factor of 1, and then show that using that procedure, following that procedure, you can end up with a photon propagator in finite volume with finite T and finite L that would essentially look like what we had before in this form, but rather with a sum over momenta of 1 over k squared factor, where the sum does not include the 0 mode. This prime actually means that the k0 term of the sum is removed. Remember, that was the problematic singular terms. And what we're trying to say here is that if you fix the gauge such that these shifted configurations are 0, they're fixed to 0, then you can follow the Faddeev-Popov procedure, get rid of infinities that arise, and define the path integral of this theory. And what that means in the end of the day is that you end up with a propagator that looks like before, except that the zero mode is removed, and therefore this is infrared regulated form of the propagator. Okay, so this is all for pure QED. What happens if I introduce the fields? Because remember, I really want these fermionic fields. They have charges, and I want to understand what happens to the gases law if I have these charges inside the volume. So let's see what happens, right? So when I introduce these fermionic charges, what happens is that I have a fermionic current. This could be their background current, background charge, or it could be dynamical charges, these fermions, right? Electrons and positrons in this theory. That is coupled to a mu, right? So this is the term that would be added to the action such that I have the full QED theory, okay? So obviously, we look at this term, we realize that this is not invariant under this shift transformation. In particular, if I take a mu and shift it by a constant, there would be an additional term added to the action, right? So we kind of break, this kind of breaks that shift symmetry that we've been talking about and proposing a solution to. But in fact, we can bring back that shift symmetry because remember, we were able to deal with the problem of shift symmetry in the pure QED by introducing a gauge fixing and by removing the full 4 momentum 0 mode of the photons from the theory. And now if I define my interacting part of the QED action in such a way that satisfies that shift symmetry, then I can implement all this gauge fixing and everything. And I have consistently a theory that if I remove this gauge, the 0 mode of the photons, then I have a fully properly regulated theory. So how can we do this? Well, it turned out that if we introduce the following term into the previous action, I'm going to call this as interacting prime now, and then we bring back the shift symmetry, and we're fine. So why is that the case? Because remember, so if we go back to this form over here, okay, so if we look at this form over here, we realize that the a mu field, the part, so let's just think about Fourier transforming this this form, right? If we Fourier transform this form, we're going to have essentially the 0 mode of the photon that is kind of coupled to some sort of a background charge, right? And remember that 0 mode is the part that is corresponding to the shifted field, right? So if you go all the way back to this a mu in the shifted a mu, you realize that the shifted part is only a contribution to the 0 mode of the field, right? And what I'm trying to say now is that therefore we have to kind of worry about the 0 mode of this field to be able to bring back the shift transformation, okay? And this is the way to do it, right? As I said, this term, which couples to the 0 mode of a mu field, if I just subtract it out, then I recover the shift symmetry that I was talking about. Okay, so that's really sort of a simple fix here, and that will allow you to have also shift symmetry invariant interacting a mu j mu field, and therefore you don't have to really worry about the 0 mode as a result, right? So then we have sort of a consistently regulated theory as a result of this. Okay, so this is all good, except for the fact that, well, what happens here is that if you think about it from a physical perspective, is that you are introducing a uniform charge, right, J mu field, or integrated J mu field over entire space, right? If you think about this, and you're introducing with a negative sign such that you are removing whatever charge that you're putting into volume to be able to satisfy the Gauss's law and everything, you're canceling it out by this the sum of all the charges everywhere, okay? And once you do that, then you don't really have to worry about the Gauss's law, essentially. Okay. But this is kind of an issue. And the reason being that, well, if you now think about, so this term is local, right? A mu, J mu, the original action or Lagrangian was local. But the second term that we are subtracting to be able to consistently remove the zero mode, consistently remove all of these charges that would require the satisfaction of Gauss's law, which is problematic in periodic boundary condition. If we do that subtraction to solve some problems, on the other hand, we're introducing a problem of non-locality because these J mu fields are now defined everywhere in a space and time, and they're coupled to another A mu field through these interactions. So now we have a theory that is non-local, and it is non-local in both space and time, okay? It couples this mu field, couples to fermions at all positions and at all times, okay? So of course, this non-locality goes away as we take the limits of t goes to infinity and L to infinity because of this kind of prefactor, right? But on the other hand, for any finite value of t and L, we would be in trouble. And in particular, the problem of time non-locality is a bit more severe because it turned out that while we do these calculations in Euclidean space-time in the end of the day, and we have to have a well-defined precision to be able to analytically continue these problems to Minkowski space. And we take advantage of the reflection positivity of the transfer matrix to be able to do this. And then once you have a time non-local theory, it turned out that this reflection positivity is out of the picture. And therefore, there are some problems or subtleties in how we can actually do this analytic continuation, for example. So while the previous work have actually used this scheme, and I'll come back to some examples of how it can work in practice, we have to be very careful about these non-localities and in what way they can change the theory for any finite T and L, and how to take the right limits such that we're not ruining very important analyticity conditions in our theories, okay? All right. Now let's talk about another solution, right? So as we saw, the previous solution would remove the zero mode of both the special zero modes and temporal zero modes of the photons. As we saw, removing the temporal zero mode of the photons would give us a time non-local theory. So then the next solution that would come to mind is that let's just not remove the temporal photon zero mode, but rather the special photon zero mode. So that would be what I call a QED left, or L, not left, L prescription as given here. You take your photons, these are Fourier modes of the photons, and you subtract the special components of the momentum, all right? So there's no photon associated with those special zero modes. I changed the notation from K to Q. Q is essentially the same as K. All right. So this means that now I still have the shift symmetry, but this shift symmetry is actually a bit bigger because I can have functions of time that would still satisfy the same essentially equations of motions, and this B mu field is not promoted to a time dependent. So these are still constant uniform in the space configurations, but they could be time dependent. All right. So then you can work it out. You can introduce now another sort of gauge fixing condition through Faddeev-Popov procedure. And then what you're going to end up seeing is that you get exactly the same photon propagators before, but except you only remove the K, special K momentum vector 0 out of the Fourier components that are being summed over in that propagator. Okay, so that's the only difference, but all the steps are very similar to what we did for the previous case that was more general, okay? And what about the interacting action? Well, now for the interacting action, we have the following form. In order to be able to decouple from these photon zero modes, then we have to really subtract out this sort of charge, integrated charge or integrated current over entire volume. Okay, again, in the limit of L goes to infinity, we recover the same theory, no problem. But for any finite L, we're coupling A mu x to essentially the psi dagger psi fields at all other positions. Okay, and what that means is that you kind of whatever charge that you have, you just take it and kind of spread it over entire lattice, and then your A mu field is kind of interacting with a little bit of that charge everywhere because there's this factor of 1 over L cubed, but it's everywhere. Okay, so now we solve the problem of time non-locality. Our photon propagator is well defined, but we haven't solved the problem of a special non-locality. Okay, so again, we have to be very careful as what kind of assumptions might now go wrong that usually we put on our quantum field theories. Usually we put on effective formulations of those quantum field theories when that effective formulation means that you think about IR physics, you think about the UV physics, there's a separation of a scale, and you safely, if there is that separation of a scale, you can safely ignore sort of those UV effects, write down an IR theory that has the knowledge of the UV effects in some low energy coefficients, as we defined in effective field theories before. And this assumption might actually break down because if we're dealing with a non-local theory, that means that your charge at very short distance is coupling to sort of these external, these uniform charges everywhere, right? So you have to be careful about that separation of IR UV physics. And it turned out that in certain situations, this can be problematic. But again, as you deal with it properly for given problems, there should be no issue. And in fact, this is one of the most popular formulations of QED in a finite volume so far, because it doesn't have the serious time locality problem. It is easy to implement. You just do the same thing as you would have done with the full QED. You just remove this special zero mode of the photons, and then you move along. Computing finite volume corrections in this formulations is also pretty straightforward for most quantities, as we will see an example of. And in particular, it has most of the symmetries of the original theory. Okay. So we'll talk about that aspect later, how we define and calculate observables in this formulation. But I want to mention another solution as well, without giving too much detail. And that's the solution that relies on changing the boundary condition. Okay. So this is called QED C star, where C star means charge conjugation. So instead of working with periodic boundary conditions, it turned out to be problematic because we're really enforcing the fields to become the same at the boundaries, so to turn into themselves at the boundaries. That's a very serious and constraining condition. How if we change it to something else, which is called charge conjugation boundary conditions? What does that mean? Instead of turning the fields to themselves as they periodically move in a space and time, we impose that they turn into the charge conjugate of themselves. Okay. And so that's interesting. That means that if I have an A mu field, we know that the charge conjugate transformed A mu field is necessarily minus A mu field. Okay. So instead of this photon field, this vector potential to actually turn into itself at the boundary, it would turn into minus itself at the boundary. Okay. And you may say, well, that doesn't seem like a big change compared to periodic boundary condition. How is it that it solves the problems with the zero mode? That would be the topic of exercise 2. It's not actually hard to see this, okay? So this is the condition that you have. If we have periodic boundary conditions, you work it out and you realize that your momenta should be discretized in units of 2 pi over L. Now, you can ask yourself how if instead of A turning into itself, it would turn into the negative of itself, what kind of Fourier modes would contribute to the Fourier transform of these A mu x, okay? So this is the topic of this exercise. What you're going to see is that actually the Fourier transform in this theory does not have the zero mode, okay? Just by construction, because of this boundary condition, those modes don't contribute to the Fourier decomposition of this field. And therefore, you can actually write the photon propagator in the Fourier space already without the zero mode. Of course, there would be different types different momenta contributing. You have to figure it out. Different discretized momenta that will contribute to this Fourier decomposition. But the zero mode is not going to be one of them, it turned out. All right. So on the surface, this may appear like a minor modification to the theory, as I said, and just changing the boundary condition, and it already removes the zero mode. It actually removes the zero mode without resorting to any introduction of any non-locality into the theory. This is completely local formation. It's the same action, everything. It's just that it's just a different boundary conditions, right? So it may actually look like a really good idea to do this. And it may be, except for the fact that you have to be careful that by doing this kind of boundary conditions, you're breaking, it turned out, both the charge and the flavor symmetry around the boundaries. So you have to consider those fermions as well and think about how they transform on the boundaries if they go into the charge conjugate of it themselves. And if you just like work out your conservation laws, you're going to realize that you're breaking those conservation laws for the charge and the flavor number as a result of these boundary conditions. Well, that seems like severe, true, but those effects are going to go away as you take the volume, space-time volume to infinity, right? So those are controlled. Those could be exponential. In fact, you can actually show that they're exponential in the volume and therefore under control in numerical simulations. But on the other hand, it's just a bit more involved situations with these boundary conditions, because certain processes that could not occur before, they are there in your calculations. You have to account for them. You have to make sure that they are numerically small, right? And so that's the caveat. So that's another solution, which is local. Can we think about another solution that is also local? Okay. And yes, we can. There is another solution called QEDM. And this is when we set the mass of the photons not equal to zero. Okay, so another pretty dramatic change to the QED theory, because then you lose your gauge invariance. But in the limits of m gamma to zero, then you recover that gauge invariance, right? So let's see how it works. Obviously, the zero mode, which is the cause of the problem with QED in a finite volume, comes from the fact that these photons have zero mass. If I introduce any finite mass to the photons, then these objects are finite range, have finite Compton wavelength, and therefore the QED force is going to be finite range. It would be like a Yukawa type potential as opposed to a Coulomb type potential, right? So what that means is that now we can fit these QED interactions inside the finite volume and not severely change their range because of these finite boundaries. But then on the other hand, we are going to have a more complicated expression for observables, because now we have a photon mass, and we have to identify how our observables would depend on this photon mass to be able to, in the end of the day, extrapolate it away to zero. Also, we have to do these extrapolations in a careful way, meaning that we have to first take the infinite volume limit before taking the m gamma to zero limit, right? So there's ordered operations, because if you first take the m gamma to zero limit, you're back to the scenario with a problematic QED in a finite volume. If you take the volume to infinity first before taking the m gamma to zero, then you recover the limit that would be realistic. Okay. And importantly, if I'm dealing with the theory of hadrons, for example, and there is some mass in the theory, like the mass of the lightest hadrons, like the pion, then you have to make sure that you set these m gamma much smaller than the mass of this hadron in the theory, so that there's a clear separation between UV and IR physics, it turned out. So there are all these like considerations once you introduce this fictitious mass to the photon. But if you deal with it properly in your numerical simulations and you take the right orders, you should be able to recover the results associated with infinite volume, zero photon mass limit of the theory. Okay. All right. So I've given a bunch of references on all of these different solutions to the problem of QED in a finite volume in the first topic page, as you saw. With that, I'm going to now just focus on one formulation. So I'm not going to give you a bunch of examples with all these different formulations, but rather focus on one primary formulations, a formulation that a lot of people have used and really see precision results with this formulation in the past. As I said, is this QED left or L. Just meaning that I'm removing only the special zero mode of the phonons. Okay. The strategy that I'm going to present here, you can apply it to other formulations as well. In fact, so that's why I'm going to just work out the examples in these formulations, and I'll mention differences when it comes to it. Okay. All right, so what do we want to now compute? Let's start from a very simple example. All right, rid of this. Let's just start from a very simple example. In fact, let's start from a classical example, because you can as well ask this question. Forget about these like quantum field theories. If someone would give you just classical E&M and ask you what happens to, say, a charged sphere if I put it in a finite volume. In other words, if I try to truncate the range of the Coulomb force beyond a specific volume. Okay, so this is not the same problem as someone would give you a box and you put your charge inside it and asking what the interactions, the self-energy, and so on associated with this configuration is. This is beyond that. It's saying that I have a box and nothing is defined beyond this box. My electromagnetic interactions only valid inside the box, nothing is outside the box, right? Or in other words, we have periodic boundary conditions. We have periodic images of that box, if you think about it, all right? So this is a very different situation. That's what we're considering here. Okay, so I'm gonna look at the charge sphere just in classical electromagnetism and ask the question of how the self-energy of this classical charge sphere is modified if it's enclosed in a cubic volume with periodic boundary condition. By enclosed, it means if the force itself is enclosed inside that box, okay? So let's look at the solution. Well, not all the steps of the solutions, because that's what you're supposed to work out on your own. Get rid of these. Okay. So here's a picture of this configuration. I have a sphere with radius r, with charge EQ, is enclosed in a finite volume, which is cubic, has periodic boundary condition, the length is L. So here I'm not considering the finite temporal extent, but rather just the special extent. I'm just assuming time is infinity. Okay, so that's a scenario that you can think of. And we are going to see that the self-energy is going to get corrected as following. Okay, so the self-energy of this, if you go back to your E&M course in undergrad, you should remember this interesting calculations that we did in an infinite volume, obviously, where you find that the electromagnetic self-energy or electrostatic self-energy associated with this configuration of charge is 3/5 of E squared Q squared over 4 pi r, where r, again, is the radius of this sphere. All right, and then Let me, okay, so then what about these configurations when the sphere is inside a box? It turned out that you get infinite number of correction terms. They are scaling as 1 over L to some power. The first contribution turned out to be 1 over L with a coefficient, which is a constant C1, defined as this interesting regulated sum over n vectors, these integer n vectors, where 0 is not one of those integers, so that's removed, minus the integral associated with that configuration of 1 over magnitude n. It turned out that this comes out to be minus 2.83729, and you can actually make the precision better and better. Okay, if you're curious where that comes from, you can check out this reference that I've given here. There are a lot of cool tricks that people have developed for dealing with these regulated sums. So you can check it out. At next order, you're going to see 1 over L cubed type contribution. So there's no 1 over L squared, but there's a 1 over L cubed turned out for this configuration. Okay, so now you ask yourself, how do we arrive at an expression like this? Well, you have to go back and ask yourself how a Coulomb potential is modified in a finite volume. And the Coulomb potential is the 1 over R potential. You Fourier transform it, it's going to be e to the I k r over k squared, obviously. Now that we are in a finite box, we're not summing over all momenta, rather we're summing over the k equal to 0, summing over discretized values of k. And in this regulated QED, we're removing the 0 mode of the photon. So that's why the sum is like so, okay? So the exercise is asking you to start from this finite volume Coulomb potential that is regulated, and then drive the self-energy of this charge sphere configuration. It's a few lines of algebra, and in one of the references that I gave in the topic page, you're going to find part of the solution at least. So if you got the stuck, you can check it out. But I think this is kind of a very interesting example, because it tells you that you can as well define the classical theory in a finite volume and ask similar questions, right? And what we see is that these volume corrections to things like self-energy would go like powers of 1 over L, as opposed to exponentials of L, right, or minus L. And that's very important. That's already a feature of the fact that these photons are freely propagating objects that can go all the way to the boundaries and explore them. And because the free momentum modes of these photons go like 2 pi over L, and therefore you should have expected this kind of volume corrections associated with the fact that these propagating photons go all the way to the boundary, okay? Which would be very different from a situation where, for example, the photons had mass and their wave function would be isolated or localized inside the volume and would not be able to really explore all the way to the volume. And therefore, you actually get exponential corrections to these observables as opposed to these volume corrections. Okay, so that's for the classical example. Something to notice is that this first order correction, if I cancel out R over here, I see that there is no kind of dependence on the shape or the properties of these objects that I put in a volume. That already tells you that there is some sort of universality associated with the leading volume corrections. And you then wonder whether you see the same feature in other objects in this theory, as well as in the quantum theory, right? If you're now going back to the quantum field theory associated with electromagnetic force, which is the QED, are we going to see the same universal, presumably, effects in corrections to the self-energy of particles or the mass of the particles? And amazingly, that's the case, turned out. Okay, so let's now look at it. So I'm going to look at let me see. Okay. I'm going to look at the mass of hadrons in the QED theory. Okay, so I have hadrons, meaning that well, I have strong interactions and so on. For all purposes, I am not worried about those strong interactions at the moment. I'm going to just ask if these hadrons, for example, have charges, and I'm going to put them in a finite volume and simulate them. What would be corrections associated with the fact that the QED part of the standard model is inside the volume? I'm going to consider corrections due to the QCD part in the finite volume in the next lecture. So let's just forget about that and just focus on the QED part for the moment, okay? So then the question is how the mass of a hadron would get modified in a finite volume with periodic boundary conditions, given that there is these long-range or infinite-range phonons in the theory. In principle, do we actually expect from a quantum perspective to see corrections to the mass of these hadrons associated with the infinite range of the theory, QED theory? And the answer is yes, right? And so where do the sort of corrections to the mass of these objects come from in quantum field theory? They come from radiative corrections usually, right? So you have your hadrons, it emits a photon, right? And in principle, this photon is virtual. It means that it could have all sorts of momenta, but for certain values of momenta, it can actually go all the way to the boundary. It could become unshell, right? That's also part of a process, a radiative process. It can go all the way to the boundary because it has zero mass, right? And then in fact come back and get reabsorbed by your hadron, right? So this is the notion of radiative correction, but in this case, it's the notion that these photons, there is the zero mode of these photons that could actually go all the way to the boundary and come back and get reabsorbed. And therefore, these photons are modified because of the boundary. And therefore, the corrections to the mass should be modified because of this, because these photons have a knowledge of the boundary and they get reabsorbed by your hadron. So that's really sort of the intuitive picture of why we should expect volume corrections to the mass of the hadrons. Okay, so now we're going to work out an example to see explicitly how this comes about. Right? So the simplest example is a scalar field. Forget about fermions for the moment. Let's say you have a scalar field like a pion, right? A pi plus, for example. And I just write down the free part of the scalar field, and then I promote those derivatives to covariance derivatives, as is usual, to have a gauge invariant theory of these scalar fields coupled to electromagnetic field. Okay, so this d mu over here has information about the a mu fields inside them, and I have also this mass term for this field. Okay, these are scalar fields. All right. Here's the definition of your covariance derivative, and you see this coupling between the scalar field, say the pion field, and the photon field, right? So then you work out the Feynman rules in the standard way for this theory. For the scalar field, I have an I over p squared ms squared. For the interactions between the scalar field and the photon, there would be two types of terms. One is proportional to the momentum, p plus p prime of this scalar field, and another one that is proportional to just the charge squared, essentially, g mu nu. Okay, so there's no momentum dependence out of this term, which is easy to see from the covariance derivative squared acting on these fields. And finally, I have the photon propagator. Let's look at the Feynman gauge that we did before. It's going to be something like g mu over k squared. Okay, and I'm in Minkowski space. All these discussions are the same in Minkowski and Euclidean space, so we don't have to worry about that. So that's why I have the g mu nu here. And for all purposes, I have all the Feynman rules that I need to look at the self-energy at leading order in the QED coupling, the alpha, where alpha is E squared over 4 pi, okay? So again, you have to refresh your mind of what we did in quantum field theory, radiative corrections. So this is sort of the mass, the self-energy corrections at leading order in this theory is going to get either a contribution from a loop like this, which comes from vertices that we introduced here, or it can come from this sort of tadpole type of diagram, this that comes from a vertex that we introduced here, this a mu vertex. All right, so then you just read off these diagrams using your Feynman rules. All right, so this would be associated with the first diagram, and this next one is associated with the second diagram. I'm not going to go into the details of this. You can look at it. You can try to reproduce it by reading off the Feynman rules. But the important thing is that, again, I'm looking at the theory where the time is infinite, but the space is finite. Okay, so that means that I still have an integration over the K0 components of this loop momenta, but on the other hand, the integration over the special momentum of this photon inside the loop is going to be replaced by 1 over L cubed of the sum over discretized momenta because of the periodic boundary condition in a cube. I'm removing the special zero mode because otherwise I would deal with an ill-defined theory. You can already see it from this 1 over K squared over here or over here. And as we saw in QEDL, we're removing the zero mode, special zero mode, to be able to deal with that singularity problem. Okay, so that's the form. Now, exercise 4 is asking to perform the expansion of small 1 over L to show that this form actually turns out to be the following: minus I sigma evaluated at P equal to 0, where P is the momentum of this external hadron, is going to have the following expansion. It's going to be a sum over momenta, except for the momentum 0, of 1 over K squared, 1 over K, and so on. And the way that you can actually arrive at this is not that hard, okay? What you're going to do is that, well, you have to perform the K0 integration in the complex plane using contour integration tricks. And then you're going to then expand in a small 1 over ml, and you're going to see this form. So just a few lines of algebra should be able to see this form. All right. So now that we have the self-energy evaluated at P equal to 0, external momentum, the special momentum, then we're ready to actually look at the mass corrections. Because again, if you remember from your quantum field theory course, the mass gets corrected by this self-energy function evaluated at P squared equal to M squared. And therefore, at order alpha, we can see that the correction to the mass, which comes from taking this sigma, and I think I have it in the next page more explicitly. No, I don't. What this delta M means, it means that it's the difference between the mass in infinite volume compared to the finite volume, okay? Which therefore is a difference between the sigma, the self-energy function, evaluated at infinite volume compared to evaluated at infinite volume. Finite volume. This is the finite volume form. Of course, the infinite volume form is going to be when this sum is replaced by three-dimensional integral over the special K momentum vectors, right? So that's what that difference means. And therefore, there are a bunch of contributions that we don't really care in the end of the day because they're going to cancel between the sum and integral, it turned out. And those are the ones that usually happen at UV. The UV physics of finite and infinite volume physics are the same, but the IR physics is different when we're trying to characterize or understand what differences it makes in IR for these observables. All right, in the end of the day, once you do this subtraction, do the math again, you're going to see that you get E squared Q squared over 8 pi L times C1, 1 plus 2 over ML, and then higher order terms. Okay, which is interesting. Where does that come from? Well, again, if you already have this form, and in the previous page, I gave you at least one example of a sum that would turn out to be the C1 coefficient. It turned out that the next sum is actually also proportional to C1, but the next ones are going to come with their own special sum integral difference and different numbers. It doesn't matter for the current discussion, but then you get this form. So it's proportional to the alpha, or E squared over 4 pi. It is also proportional to that C1 number that we saw in the classical example of a charged sphere. And at leading order, in fact, it looks exactly the same as, because the R cancels, you get 1 over L proportional to C1, E squared, Q squared over 8 pi. So indeed, even in the quantum theory, the corrections to the mass seem to be universal at leading order. Okay. So that's very interesting. Let me get rid of this and this. But this the next order correction is 1 over L squared. And if you go back to this example, there was no 1 over L squared. Okay. Great. So it turned out that in the quantum theory with gauge invariance, you can show that order 1 over N and 1 over L squared corrections are going to be universal. They're independent of the spin structure of the particles, for example, and independent of other internal structure properties of these objects. So that's a very interesting result. But the higher order corrections are actually not independent, and they are not universal, it turned out. Okay. In fact, in exercise 5, you're going to see that if now you start from the Dirac theory of fermions coupled to electromagnetic fields, the actual QED for electrons and positrons, and you look at the finite volume corrections to the mass at order E squared and E squared over L and L squared, those corrections are going to be exactly the same as what you have here. Okay, so that's for the next exercise. So again, the considerations are very similar. You have to go back and remind yourself how you do the self-energy of electrons in QED in general at leading order. So you have to remind yourself of all that gamma matrix technology and everything else. But then you go back in a calculation of infinite volume self-energy and turn a bunch of integrals into sums, and you reprocess them again in the same way that we did it for this scalar field theory. So again, it would be interesting to see these corrections, and we see that they're actually the same as the scalar field theory, at least in this leading order 1 over L and 1 over L squared corrections. Okay. All right, so now you may ask, what about these other formulations? I focused on this particular QED-L formulation. What about other formulations? Well, how about, for example, QED-TL? The very first thing that I introduced, that was time non-local and the space non-local. Well, what you're going to see is that you go back in the calculations that I showed, and instead of having a sum over only a special momenta, you will have a sum over both special and temporal momenta, and you remove the 4 momentum 0 mode of the out of that sum. That's QED-TL. That's the only difference, right? And then you come back, you look at this whole in this whole calculation, you do a similar process all the way, and what you're going to see is that, well, you're going to see again this C1 factor, and you're going to see 1 over L corrections. They're slightly different. But then importantly, at order 1 over L squared, you are going to see, at order 1 over L cubed, in fact, you're going to see also a dependence on this temporal time. Okay. And now you see kind of some of the problems with this formulation, because if T goes to infinity first before L goes to infinity, right, then these finite volume corrections to the mass are going to be diverging, right? They're going to be very large. And that's a problem. That's problematic, right? In other words, you have to be always in a regime where you take the limits properly. Okay. So you have to first take essentially the L to infinity limit, and then take this T to infinity limit. So that's sort of a feature that we have to worry about for this formulation. It wasn't a feature that we had to worry about here, it turned out. And That didn't stop people to actually work with that formulation. In fact, if you make sure that your volume is essentially large enough such that the mass of the lightest hadron, in this case, the hadron that we're considering in this theory, that the pion times L is much smaller than 1, you can make sure that this problematic term is actually numerically small. And I think that's what people did in all these previous papers. With QEDL, though, you have a sort of a more control over these finite volume corrections that can actually be smaller. In fact, there have been very precise calculations of proton-neutron mass difference from lattice QCD plus QED. And that proves already that QED left is a very powerful regulated QED formulation in a finite volume that can give rise to the results that then match with the results we see in nature. Why this observable? Because, well, remember, protons have charge, neutrons don't have charge, but they have associated quarks and gluon, and the quark degrees of freedom that have charge, although as an object they're neutral, but they have these quarks that have charge associated with them. So QED would impact the masses of these objects in different ways. And by the way, if you have both QED and QCD in the formulations, everything is non-perturbative. You have to calculate all these masses at the same time. And the corrections due to the finite volume associated with QCD and QED both should be accounted for properly. And once you do that, and you do that using this QEDL formulation, for example, you would be able to quantify all these volume corrections and then correct for them. And what you see in the final answer, again, is something that matches with experimental value. So that's really great and shows sort of the progress that's been already happening in this field, despite all these problems with QED in a finite volume. If we have the proper regulated form, in principle, we can compute observables and get rid of those volume corrections, and then take the infinite volume limit in a systematic way. Another sort of notion is that in all these calculations, now you can imagine how those calculations would change if I have other formulations, right? And for example, if you have the QED C star, the C star boundary condition situation, then instead of having a sum over all these discretized values that are consistent with periodic boundary condition, you're going to have sums over other values of momenta that are consistent with this charge conjugation boundary condition, it turned out. So the values of those sums are going to be different, but the strategy in dealing with these sums and these analytic forms is pretty similar. Okay. What about QED-M, when the mass of the photon is set to a finite value? Well, again, things look similar. I have infinite, still I have discretized integrals over here. But on the other hand, the K squared, the momentum of the photons in this term and this term is going to be regulated with the mass of the photon, right? So that would look like essentially sort of a scalar field theory propagator with a finite mass. That means that these sums and integrals are going to be more complicated, but you have techniques to deal with them. And then you end up with volume corrections to the mass, not only would depend on L, but also the mass of the photons. And as I said, you have to take the limits properly such that you achieve the infinite volume limit without any problem, any singularity problem associated with the finite volume formulation. And then really the last topic that we're not going to talk about, but I want to mention at least another observable that you can imagine calculating finite volume correction of, which is an important object, it turned out, for the sake of lattice QCD computations, and that's the anomalous magnetic moments of, say, electrons or muons, okay? Because this is an object that we're calculating nowadays with precision in lattice QCD to be able to confront experimental measurements. That's a very active frontier. But if we want precisions, at some point, we have to include QED in the picture. And this exercise is going to and this is a bonus exercise, but it's not that hard. You can go back and ask yourself, what is the leading order corrections, QED corrections to the anomalous magnetic moment? And if I put that inside the finite volume, then what would be finite volume corrections associated with that? And what you're going to see is that, again, you're going to see 1 over L corrections or 1 over MUL type corrections. And these are pretty large. So if you're after 1 part per million precision, for example, in this quantity, you can find out what volumes you need in your lattice calculations to achieve that. And once you get that number, that might discourage you because this would not be something that we can get at any of the future lattice calculations. But something that you remember is that we're not really directly calculating muon magnetic moment and QCD, QED. What we're doing is we're calculating the hadronic contribution to muon magnetic moment diagram. And those are either hadronic vacuum polarization or light by light sort of scattering type diagrams. And the finite volume corrections to those objects is much smaller. Okay, so you still have to control it and so on. But it turned out that they're much more under control compared to if you wanted to just perform a QED, QCD, full calculations of the full thing, the full object, put your muon in a finite box with QED and QCD defined properly, and compute its magnetic moment. Then the finite volume corrections are like this, and they're going to be very large. But this is not exactly how we do these calculations on a finite volume. Okay, so if you're up to it, go ahead, draw the diagram in QED, just the leading order diagram associated with the magnetic moment, which is your essentially QED vertex function, and then see what happens if you compute that diagram with discretized momentum sums that are regulated by removing the zero mode. Okay, and this is QEDL formulation. All right, that being said, I already mentioned some of the progress in these lattice QCD QED calculations that are happening. We have started over a decade ago. There's been a lot of really nice calculations of the masses of hadrons, the mass splitting between hadronic multiplets, which is a very, like proton and neutron, which is a very small number. It really depends on these QED corrections being taken into account properly. There's been also calculations of hadronic decays, including QED, like leptonic decays of mesons and so on, and that involves QED corrections and so on. So this is a very active frontier. Corrections due to QED, to muon magnetic moment, hadronic vacuum polarization, and so on. This is another subject that has been really explored in the past and studied very, very well in the past few years. And sort of on the formalism side, there are still a few things that we need to figure out, and how to deal with the charged particle scattering in a sort of model independent way, how to deal with decay and transition amplitudes with initial and final charge states, and so on and so forth. These are still evolving topics, and people are coming with better and better schemes to control volume corrections and be able to get infinite volume observables out of these QED finite volume calculations. And that being said, this is still a pretty active and live field. If you're interested in these both numerical and formal developments in this topic, you can really get involved and contribute. All right. Thank you very much. We'll continue with lecture 2, which is about QCD finite volume corrections to single hadron masses.